Welcome back, everybody. Hope everyone is doing okay. I just wanted to upload Monday's lecture notes for you guys. We're going to be talking about the geometry of 2x2 systems. There's going to be a little bit of information in here that will help you with the Maple quiz this week. So we're going to talk about the Maple quiz that's due on Friday. And this will also get you started for the quiz on Friday. We're going to have 2 days of lecture here on Monday and Wednesday that'll prep you for those two things that are due on Friday. And then Friday, we're actually going to start the next unit of material, and we'll have our first exam next Monday. I'll have more to say about the exam coming up later in the week, so just keep an eye out for that. I do want to let you know that I have graded your most recent quiz, so this would be quiz 6 is graded, and the results are out there for you to look at. Hopefully I was able to give good feedback on those so you can kind of know where there's any points that you're messing up. Remember, we do have office hours from 1 to 3, Monday through Thursday. If you have any questions for me, as you can see, I haven't graded Maple Quiz 6 yet, but I probably will get to that either today or tomorrow. The announcements for this week, I do have lecture videos for March 30th through April 3rd. The announcements are up for that. We are going to be the first part of the week. We're going to be dealing with the trace determinant plane. So the notes that we talk about today, those notes are going to get you into the rest of the week. And I actually do need to go back and make a change here because we're not going to start second order linear equations till Friday, and then reduction of order method will be the following Wednesday. So we're a ways away from that, actually. We're going to do nonlinear systems here in between. So I need to go back and make a couple of changes there. But you do have the quiz and the Maple quiz due this week, and you need to be thinking about your projects. You're going to do a screencast or some kind of video presentation over whatever your topic is. Take a look at those. Take a look at the details for that project and make sure that you're aware of that. I believe those are due not this Saturday, but next Saturday. I think April 11th is the correct date for that. The exam 2 material is going to be coming up real soon. You'll start to see me make some changes to this to accommodate our new exam, but I'll talk more about that later in the week. All right, so let's take a look at the notes for today. So what I would like to accomplish today is an understanding of the geometry of all the eigenvalue stuff we've been doing lately. So we've talked about real eigenvalue problems, repeated real eigenvalue problems, and complex eigenvalue problems. And I want us to kind of tie a neat bow on that topic and make sure that we understand geometrically when we solve these linear systems, what do they look like in the phase plane? How can we anticipate what they look like in the phase plane, and how can we use that to analyze the systems? More importantly, you worked on this on the most recent Maple lab where you had to go in and do the eigenvalue problem, plot phase portraits and all that for all these different linear systems. We're going to dive into that a little bit more deeply now that you've experienced that, and talk about some of the things that are going on there. So just want you to recall that if we have a 2x2 linear system, in other words, if we have, say, A is equal to the matrix A, B, C, D is its coefficient matrix, then we know that the characteristic equation is given to us by lambda squared minus the trace of lambda plus D. This is only in the case where A is 2x2, right? So we're only dealing with 2x2 systems today. And so lambda squared minus the trace would be A plus D. The determinant would be AD minus BC. So this is the form that our characteristic equation takes. And the usefulness of this characteristic equation, we know, is that the zeros of this are eigenvalues. And so I want to use that to our advantage to talk about all possible solution behaviors of a 2x2 linear system with constant coefficients based on the association between eigenvalues and coefficient matrix A, B, C, D values. Let me explain. If I tell you the characteristic equation is lambda squared minus A plus D lambda plus AD minus BC. At this point in the course, you have no problem with that. What if I tell you that the matrix A has two eigenvalues? Now, I'm not going to tell you if they're real. I'm not going to tell you if they're repeated. I'm not going to tell you that they're complex. I'm just going to tell you it has two eigenvalues, and I will call them, for right now, lambda 1 and lambda 2. If that's the case, then it makes sense that whatever this quadratic function factors into, it must have roots lambda 1 and lambda 2. So this characteristic equation must factor into lambda minus lambda 1 times lambda minus lambda 2. If I then FOIL that back out again, this is lambda squared minus lambda 1 plus lambda 2 times lambda plus lambda 1 times lambda 2. And what I want you to do is make an association with the fact that this term here represents this term here, and similarly, this term here represents this term here. So what you can immediately say from comparing those two is that the trace of the matrix A is equal to the sum of the eigenvalues of the matrix. So whatever the two eigenvalues are, if you add the two eigenvalues together, you get the trace. Look, they take the exact same spot in the characteristic equation. Similarly, if you go to try and find the determinant of the matrix A, remember this is the determinant here, that's the product of the eigenvalues. So the product of the eigenvalues for a system is equivalent to the determinant of that system in the 2x2 case. So using all that to our advantage, see if I can make this nice enough. I'm going to plot kind of an interesting plot here, something called the trace determinant plane. So along this diagonal, I will list the trace of the matrix. And along this along this axis, I will list the determinant of the matrix. So this is called the trace determinant plane. Now, before I get into that pretty heavily, there is one more small thing to say here. And that is, not all values of the trace and the determinant are created equal. There are some values of the trace and determinant that are really important. For instance, if I said that my characteristic equation is lambda squared minus, I'm going to use capital T to represent the trace of the matrix, plus I'm going to use capital D to represent the determinant of the matrix, then we're solving for eigenvalues by setting that equation equal to 0. I can then find the zeros of that equation by using quadratic formula. In other words, let's use quadratic formula to determine the eigenvalues in terms of the point TD that we would want to plot in the plane up here. So if I use the quadratic formula, I would take the opposite of b, so it would be t. So lambda is equal to t plus or minus the square root of b squared minus 4ac over 2 times a. And what is particularly interesting about this is that here lambda is t over 2 plus or minus. You end up with this, we call it the discriminant. It's the value inside the radical, inside the square root here. So the discriminant of this root is t squared minus 4d. It's also something known as the critical polynomial, because we're super interested in anywhere this quantity is 0. The reason we're interested in where this quantity is 0 is because if you're just a little bit above 0, you have real roots. We know what real roots look like for eigenvalues. If you're a little bit less than 0, then you have complex roots. And if this quantity is equal to 0, we know we get repeated roots. In other words, this is the critical polynomial because it critically separates 3 different types of behavior that we've seen in these eigenvalue problems. If I wanted to plot this critical polynomial, remember the vertical axis here is the determinant. So I could simply take d and set it equal to, it would be t squared over 4. So I can think of this as the polynomial x squared over 4, and if I were to plot it, let me use a different color here. If I were to plot this polynomial, it would look something like this. Let me make that a little bit flatter. One more try. All right, there we go. That's better. So this is the critical polynomial d equal t squared over 4. So think of it this way. If we want to talk about where different behaviors are, that's really easy to do by plotting the different trace determinant values on this plane and then saying, well, if your trace determinant value falls down here, this is what kind of behavior you have. If the trace and determinant point is up here, this is the kind of behavior you have. So for example, let's just start with d less than 0. Okay? So let's think about what it takes to get a determinant that's less than 0. So if your determinant is less than 0, then remember, here's the determinant in terms of the eigenvalues. A determinant less than 0, a determinant less than 0 means that lambda 1 times lambda 2 is less than 0. So how do you get lambda 1 times lambda 2 less than 0? Well, that means that you have one of the eigenvalues is negative. One of the eigenvalues is positive. I don't care which one, I just know that one's positive and one's negative. So lambda 1, for the sake of generality, let's say lambda 1 is positive, lambda 2 is negative. I know they have to be real because if you have a complex root, they're complex conjugates of each other, so one of them is not positive and the other's not negative. The determinant in this case must be this form. So which kind of solution behavior have we talked about so far, where you have one positive real root, so positive real root, and you have one negative real root? Now keep in mind, the reason that I know that these are real roots once again is here, if I'm looking down here, the determinant being less than 0, so I've got a negative determinant here. Do you see that this quantity is real no matter what the trace is? Right? Because if d is negative, a negative times a negative makes that positive, plus t squared is positive. I must have real eigenvalues in this case. So I know I get one positive real eigenvalue, one negative real eigenvalue, and we've talked about that before. Those result in saddles. So I know that everything down here is a saddle. Everything. If your determinant of your system is negative, you automatically have a saddle. All right, that's kind of interesting. I don't know that I like that. Let me make it a little bit better here. So these are all saddles. Okay, let's take a spot, say over here. So if we're looking over here, what do we know about this area? Well, we know that the determinant is less, the y value is less than t squared over 4, right? So the critical polynomial has y values t squared over 4. We're less than that value. So if you're in here, your determinant is less than t squared over 4, which is the same here. The determinant is less than t squared over 4. But it's bigger than 0. So you're bigger than 0. Bigger than 0. Now, the only difference between these two is over here the trace is positive. So over here the trace is positive, but over here the trace is negative. So let's think about what that looks like. For starters, if your determinant is less than t squared over 4, then this quantity is less than t squared, which means you have real roots. So we know we're in the case where we have real roots. The roots here are real. The roots here are real. Let's think about what it means for each of these areas to have, say, trace negative or trace positive. So if you want to have a negative trace, okay, so what do the eigenvalues look like? We're down here, right? We know we have real eigenvalues. We have 2 of them, right? We have 2 of them because it's real here. One of them, the real part, is positive because the trace is positive. The real part is negative because the trace is negative. So if our trace is negative, you have real eigenvalues that have a negative trace, which means they have a negative real part, right? So that negative real part is that negative part out front is the decaying exponential. So these decay over time because the trace is negative. So what kinds of behaviors have we talked about that have a decaying sink-like behavior, but they're real? Well, these are the nodal sinks. And similarly over here, since the trace is positive, these will increase over time because you have a positive exponential because your eigenvalues are positive. So since that's the case, then this is a nodal source. All right, so let's go inside the critical polynomial. All right, if we go inside the critical polynomial, we're looking at values where the determinant is greater than t squared over 4 in both cases. And since the determinant is greater than t squared over 4, then we know that this is complex, so we're looking at complex conjugates. Here, this sinks, so this will also sink because the sink part is based on the trace, and so if the trace is negative, the real part of the eigenvalue will be negative, and so you get a spiral sink in this region. And in this region, you get a spiral source. Now, there's still more behaviors to talk about. What happens if I'm on the axis inside the critical polynomial? If I'm on the axis down here, I'm a saddle. But what happens if I'm at this point right here? Well, if you're anywhere on the positive d axis, then you know that your trace is 0. And if the trace is 0, what do you end up with? Well, you have a complex root because you're inside this complex root with no real part. Those are the perfect periodic solutions that we've talked about. Those are centers. This is called a center behavior. It's just a periodic closed circle in the phase portrait. All right, what if you're somewhere on the critical polynomial itself? Say, for instance, you're a point like right there. Well, these points are on the critical polynomial, which means that the discriminant down here is 0. So if the discriminant is 0, you get a repeated root. You get t over 2 is repeated twice. So you get a repeated root, but the trace of that root is positive, so it's a source, not a sink. So you get what are called, these are called degenerate source. Okay, and similarly over here, since the trace is negative over here, but you're still repeated root, you get what are called the degenerate sinks. All right, if you want to have an eigenvalue that's 0, then either lambda 1 or lambda 2 is 0, right? And if lambda 1 or lambda 2 is 0, then the product of lambda 1 and lambda 2 is 0. So the determinant would be 0. And if you have a 0 determinant, then you are right here along this axis. So anywhere along the axis, say right here, this is a 0 eigenvalue problem, but it is unstable. In other words, you have a line of equilibria that are that you're moving away from. And over here, if you're on the axis, then once again you have 0 as an eigenvalue, but you have a stable set of equilibria. All right. We've talked about every possible behavior except the behavior at the origin, which is 0, 0. That is not a behavior that we care about, because if both your trace and determinant are 0, then that means both of your eigenvalues are 0. And if both of your eigenvalues are 0, it means your whole system is 0. It's a trivial example. So what we have here is a complete description of every possible behavior of a linear 2x2 system based on that system's trace and determinant. So I'm going to work through a couple of examples to show you how we can use this real quick. Do want to let you know that there is an image like this in the notes, and the textbook probably has an image like this as well. These are our spiral sinks, spiral sources, centers, nodal sinks, nodal sources, and saddles. Those are the main ones, okay? The repeated eigenvalues lie along the critical polynomial. All right, so this is the kind of example you could expect on a test or a quiz, what I need you to be able to do with this information. So I'm going to read the question, then I'd like you to pause it, try it yourself, and see if you get it correct. So suppose a linear system of equations has a trace determinant parameter plane point of 3, 2. What is the behavior of solutions to this system? All right, go ahead and pause it. Try it yourself. All right, if you haven't paused it yet, please do so. I'm going to take a look at this one with you. So let's see here. If we know the trace determinant is 3, 2, then I know that because the determinant is 2, which is positive, I know I'm not a saddle, okay? So I'm not a saddle, which means I'm dealing with the top part of the trace determinant plane. And what I have to figure out is, am I inside the polynomial where the complex behaviors are, or am I outside the polynomial where the real behaviors are? So remember, the critical polynomial is d equal to t squared over 4. So I'm going to compare d, which is 2 in this problem, to t squared, which t is 3, over 4, which is 9/4. So comparing those two is, how does 2 compare to 9/4? Well, 9/4 is a little bit bigger. So we have in this case that the determinant is less than t squared over 4. So if our y value is lower than the critical polynomial, then we must be a real behavior. So we know that this implies that we have a real nodal behavior. It's just a question of whether it is a nodal sink or a nodal source. Remember, sinks have sinks have negative traces, because they are the coefficients of the exponentials. So negative trace would be a sink, but here we have a positive trace. So it's the fact, since the trace is greater than 0, we're left to conclude that this is a nodal source behavior. So nodal source, C, is the correct answer. All right, let's try another one, very similar to the one we just did. So I'll give you a second to stop, see if you can figure out the answer, then we'll talk about it together. All right, if you haven't paused yet, please do so. This one's actually pretty easy. If I know the trace determinant is, let's say, 0, 16, then I automatically know that my trace is 0, which implies that I'm either a saddle or a center. I'm a saddle if my determinant is negative. I'm a center if my determinant is positive. Well, it's got to be center because the determinant here is 16. So we do have a center behavior for this one. Really easy. If it had been 0, negative 16, it would be a saddle. All right, so that's how you use the trace determinant plane. There are many examples just like this that I could go through, but that's the basics. What I want to do now is make sure that we understand why these behaviors look the way they do in the phase portrait. So when you plot these in Maple and you come up with the phase portraits and you look at them, why do these systems end up looking the way that they do? So I'm actually going to work with you here to sketch by hand a couple of solutions to these different problems. So we're going to start with this system here. We know that the characteristic, or that the coefficient matrix for this system is -1, 2, 0, -3, which means because this is an upper triangular matrix, we don't have to do a lot of work here. We automatically know that the eigenvalues are -1 and -3. So I'll call this lambda 2. So since those are eigenvalues, we know both of the eigenvalues are negative, which means that we have a nodal sink behavior. Now the question is, how do we plot the behavior for the system? So I want to sketch the phase portrait of the system, including all straight line solutions. And when you see straight line solutions, first off, if you haven't read it, you should read through section 3.2. But second off, as soon as you see straight line solution, what you should be thinking about is eigenvector. Eigenvectors, real eigenvectors, are straight lines in the phase plane. So if I want to plot the straight line solutions, which is always the first thing you should do with a system that has real eigenvalues, you should begin that by finding the eigenvectors. So I'm going to find the eigenvectors for my system. We've got two cases here. The first case, lambda 1 equal -1. So my system becomes, let's see, I'm adding 1 since I'm subtracting a -1. I'm adding 1 to the diagonals. So adding 1 to the diagonals. All right, so that looks just about right. Okay, so if you're adding 1 to the diagonals, this is what you would get. In this particular case, any multiple of the first column will work. I simply have to zero out the second column. So the easiest thing for me to do here is, let's say 1, the easiest thing for me to pick here is 1, 0. So 1, 0 is going to be my eigenvector there. All right, case 2. Let's find the second eigenvector. So lambda 2 is -3. I'm going to be adding 3 to the diagonal, so 2, 0, 2, 0. All right. Okay, so in this case, we're going to see that alpha 2 is, all right, so I need these to zero out. So I need to subtract column 1 and column 2. So if I take column 1 minus column 2, or 1 times this column minus 1 times this column, that'll give me 0, 0. So 1, 1 would be the correct eigenvector. All right, so now that I have my two eigenvectors, I'm going to plot them on this graph. Now you might say, well, how do you plot eigenvectors? Well, it's a vector, right? So 1, 1, you go over 1, up 1. So x1, y1, right? So the vector 1, 1 is the vector here. Let me plot these in, I'll do purple. So there's the vector 1, 1. And we'll talk about the solution here in a second along that vector. Let me get all my vectors plotted. The vector here is 1, 0. So x is 1, y is 0. So x is 1, y is 0. Is this direction. So this is the vector 1, 0. Now, you may be asking, well, why didn't I just stop like you do with a normal vector and say 1, 0, right? I could have easily just said 1, 0 is this vector here and drawn an arrow. Well, the reason is because this vector, the length of the vector that points in the 1, 0 direction, changes over time, right? So for this solution, that vector changes over time. So I'm showing all possible lengths of that vector in the 1, 0 direction. Here I'm showing all possible lengths of this vector in the 1, 1 direction. And the reason that we know that is we know what the solution looks like, right? We know that the solution to this system is a C1 alpha 1 e to the lambda 1 plus C2 alpha 2 e to the lambda 2. So we know that this is what the solution to the system looks like. And so for values of t, these are scalar multiples, the exponentials scale the vector. So if t is 0, you just get the vector 1, 0, and that's that nice little vector I had drawn. But if t is 10, that vector's quite a bit shorter. If t is negative 10, that vector is quite a bit longer. Similarly, I can have negative scaling factors because of the C1 and C2, right? I know that for different values of C1 and C2, I can scale in the negative direction. So rather than my vector pointing in the positive direction here, I could scale in the negative direction. So what you need to do to make that a part of what you're working with here is take your vectors and extend them the opposite direction as well. This is not the vector 1, 1 anymore. It's the vector negative 1, negative 1. The vector negative 1, negative 1 would come about if C2 were, say, negative 1. So imagine C2 were negative 1, then you would get the vector negative 1, negative 1 times some scaling here from the exponential. Similarly here, 1, 0, its opposite is negative 1, 0. Just negate it. And this gives you the vector in that direction. So here the idea is we have straight line solutions. And what I mean by that is if I have an initial value and I start on any of these vectors, then over time I stay on these vectors. And in fact, over time, because the magnitude of all the vectors heads to 0 over time, I know that if I start on one of these vectors, then over time I'm going to move towards 0, 0, because both the x and y components here are moving towards 0, 0. So this will lead us oftentimes to draw in arrows, like so, that indicate the direction of motion along the vector. It's just like drawing arrows when Maple draws arrows in the slope field. We're just drawing arrows along this solution to indicate the motion that we have. Here, it's not continuing in the same direction over here. It's still collapsing to 0, 0, because even if C1 or C2, let's say, is negative, and I start out on the vector negative 1, 1, over time, the length of that vector gets smaller, so I get pulled back in towards 0. And I'm not going to draw as many arrows on this side. We just know which direction this thing is heading. So we know that everything is collapsing down to 0, 0 over time. 0, 0 is always the critical point or equilibrium point for these 2x2 constant coefficient systems, which makes me very happy because I know that I have a sinking kind of behavior, so all the solutions are going to sink down towards 0. So this is definitely a sinking behavior or a stable behavior. The question is, how do solutions sink over time? For instance, suppose I had a point here. Suppose my initial condition is right there. What is that point? How does it come in towards 0, 0 over time? Does it just go straight to 0, 0? Does it bend this way and then curl in? Does it bend this way and curl in? Well, those are questions that are answered by the relative magnitudes of the lengths of the vectors here. For example, which vector, 1, 0 or negative 1, 1, because the solution is going to get closer to one of those over time, which one of these two vectors does it get closer to? And the answer is a solution over time will get closer to the vector which has more pull, which means the vector which is larger in magnitude. Now be careful here. It's maybe not what you're thinking, because out of these two vectors, which one has more magnitude? Well, as time goes on and you're pulled in toward the origin, this one gets small very, very quick compared to this one. E to the negative t dominates. It's the bigger of the two as time goes to infinity. So the 1, 0 vector is always going to be bigger in magnitude compared to the 1, 1 vector as we approach time equal to infinity. So we are going to actually get pulled closer to 1, 0. And then the opposite is true away from the origin. If we go back in negative time, this one is much bigger for negative values of t. So we're going to get pulled in toward the bigger one, which is 1, 0, as we approach in. But as we approach away, we're going to get pulled parallel to negative 1, which is the larger one away. So for example, here, we're going to get pulled into this one, but as we get further away, we're parallel. What about, say, a point here? Well, we're going to get pulled into 1, 0, which is the bigger one, but as we get further away, it's not going to pull that much. You're going to get pulled slightly in, and as you move away, it's going to become parallel. Say a point over here, it's going to get pulled in toward this one, toward 1, 0 on this side, which is this one. And further away, it looks like this. So further away, it looks like that. And then over time, it gets pulled in like this. So over time, time being positive, all of these are filtering down into the point 0, 0. And I encourage you to take out Maple for a quick second, plot this phase portrait, and see if you don't get something that looks exactly like this. If you have a point in here, it's going to be parallel at here, but over time it's going to come in along that vector. So this is what the phase portrait looks like in the nodal sink behavior. So this is textbook nodal sink behavior. I ask you to read your textbook. Section 3.2 will talk about this quite a bit more. All right, we'll do a similar thing here, and since we know what's going on a little bit better, if you want to pause and try it yourself, you're welcome to. I'm going to work through it kind of quick, since we just did an example like this above. So my coefficient matrix is negative 1, 3, 5, negative 3. So I need to find my eigenvalues. So my characteristic equation is p of lambda equal lambda squared minus the trace. The trace of this matrix is negative 4, so minus negative 4 is positive 4. The determinant is 3 minus 15. So 3 minus 15 is negative 12. I believe that's the case. And so, let's see, we've got, I think it's lambda plus 6, lambda minus 2. So let's just double check. 6 minus 2 make 4. 6 times negative 2 makes 12. Yeah, so that's good. So lambda 1 is negative 6, and lambda 2 is 2. We know we have two different eigenvalues. One's positive, one is negative. We know we have a negative determinant. Remember the determinant here? So we know we have a we know we have a saddle behavior. Now, just because you have a saddle behavior, that doesn't excuse you from finding the eigenvectors. Any of these any systems with real eigenvalues, you need to find the eigenvectors so you can plot the straight line solutions. So let's deal with, say, case 1. Case 1 here, lambda 1 is -6, so I'm adding 6 to the main diagonal. It's not surprising the system ended up like that. This is the special value that makes the system redundant. All right, so I'm going to choose some whole numbers here if I can. So my eigenvector, if I take 3 times this column and -5 times this column, so 3 times the first column, -5 times the second column, that will work out just fine. Want whole numbers so it's easy to plot on the grid below. All right, my second case here, let's say lambda 2 is 2. So I'm subtracting 2 from the main diagonal. So subtract 2, subtract 2. Once again, this is a redundant system. I can take, let's see, this one's not quite as easy. I think you just add the columns together, right? Yeah. If you just add the columns together, you see that it zeroes out. So if I have 1 times the first column, 1 times the second column, add them together, everything zeroes out. All right, let's plot our eigenvectors real quick. So the first eigenvector, 1, 1. Right here. So there's my eigenvector 1, 1. I'll plot its negative as well. -1, -1. Now let's ask here, along these lines, excuse me, along these lines, do we come in toward the origin or do we go out toward the origin? And the answer is neither. Some of them we come in, some of them we come out. You've got to test each one. So for example, the solution that corresponds to this eigenvector is 3, -5 e to the eigenvalue, which is -6t, right? So because that exponential is negative along this eigenvector, over time, the magnitude of the vector will get smaller. So this is where my sinking behavior is coming from. And this one is y2 is 1, 1 e to the 2t. So over time, unlike the last example, this vector will get bigger over time. So the arrows here should be pointed away from the origin because over time, the vector extends and becomes larger. I'm really just thinking of these arrows as as showing sort of where the vector is at different time snapshots. Over time, this vector will increase in size. Similarly, the other vector is 3, -5. So 3, -5 right there. Let's see if I can do that. Close. So there's 3, -5. Remember, this one over time we get closer to the axis because it has the negative eigenvalue. And its opposite would be -3, +5, right? The opposite is negate both, right? So -3, +5 would go through that point. This would go through right there. So right there. So this would be -3, +5, and we would collapse or sink in along this point. Well, you can see now where the saddle behavior, the term saddle, comes from. If you start in any of these 4 regions, you can't make it to the origin because as soon as you come in along 1, right? So this one, as you head toward t equal to 0, as you head toward t equal to infinity, this one's pushing you away. This one is bringing you in. So as you go, like say you start right here, over time you're going to fall in line with this one, which is much bigger out here, but you're going to get pulled in. Whoops, I said that wrong. well, no, I said it kind of right. If you start here, you're going to go out this direction parallel to this one, but in this one you're going to come in, and there's some point here where this vector has more pull than this thing which is trying to pull you in, and it bounces you away from the middle. So you're going to get behaviors that look like this. You know, say you start right here, you're going to be pulled in real close, but then, oh, I'm getting close to this vector and it's pushing me away, and you do this sort of behavior. So all of these saddles they're really easy to draw the phase portrait for once you have the eigenvectors up. So this is the kind of behavior that you would expect to see if you were to plot this in Maple. Remember, none of these lines can touch each other. These are all solutions that I'm plotting. So they cannot touch each other. And this is the saddle. This is what's called the saddle kind of behavior. You have a saddle point here. All right. So what we end up caring about the most in these examples is the concept of stability. The idea of when is a system stable, meaning over time it heads toward an equilibrium. So when we talk about the stability theorem, what we're talking about is the critical point 0, 0, and whether or not over time do solutions approach the point 0, 0. Well, we've seen various behaviors today, and what the theorem says is exactly the behaviors that we've witnessed, and that is this system we've been working with today, right, in matrix form, we write it this way. This system we've been working on today is stable if and only if both roots of the characteristic equation have non-positive real parts. Okay, where is that coming from? Well, if you go back up, we calculated the eigenvalues in terms of the trace and determinant earlier, and we determined that it was t over 2 plus or minus the square root of t squared minus 4d all over 2. And what this theorem is saying is the only way you get stability, so stability implies that t over 2 is negative or that t is negative. So you only get stability where t is negative and where d is positive, because you don't get any stability in here unless d is positive, because that saddle behavior we just witnessed has no stability. So stability implies that t is less than 0 and the determinant is greater than 0. The only place that that occurs is in quadrant 2 of the trace determinant plane. Let me go back up to our picture we made together. So this one will work. What the theorem is saying is the only place where you get stability is up here. So this is a stable region of behavior. So this is our stable region of behavior. And technically you do get stability on this axis here. You can't say that you get stability along this axis because these don't spiral into a point, but these spiral into a line, so it's kind of like stability, but honestly it's really just quadrant 2, not including the axes, is where you get stable behaviors. So they will collapse to a single point over time. In the case of these, everything in this region collapses to 0, 0 over time. Even the repeated cases, which are degenerate, they will, but they'll do it along one eigenvector only, not along 2. Because there's only, remember in the repeated case, you have a generalized eigenvector, which isn't actually a solution. So you only have the one actual eigenvector that things can come in along. All right, one last problem to discuss, and this problem is going to help you get into your Maple lab this week. So take a look at The Maple Lab for this week, it's posted. Take a look at this question and then take a look at the Maple file I'm about to show you. And that should get you started working on the first question on that Maple Lab. Suppose we have, I think that's supposed to be A. Suppose we have a system below with a parameter alpha, and we want to observe what happens as the parameter alpha changes. So in other words, suppose this can be different numbers, 2, 3, 5, -10, whatever. It can't be a variable, but it is a parameter. So I can change its value at the start of each system. And I want to talk about points of bifurcation. So remember from earlier in the semester when we talked about bifurcation, bifurcation occurs at any point where the nature of solutions change. Okay, well we know from experience that there are really all these different behavior types in the trace determinant plane. So if we move from one region in the trace determinant plane to a different region, then we've created a bifurcation because our solution behavior has changed. So what we can do is look at the eigenvalues of this system in terms of alpha and talk about the behaviors that occur. For example, so this system is of the form A equal to -1, 2, -2, and alpha. So the trace of the matrix A is -1 plus alpha. The determinant of the matrix A is, let's see, -1 times alpha minus 2 times -2, which is negative alpha plus 4. All right, so my point in the trace determinant plane is -1 plus alpha, comma, negative alpha plus 4. And we know from the formula just above that the eigenvalues we have will be t over 2 plus or minus t squared minus 4d over 2, which would be -1 plus alpha over 2 plus or minus -1 plus alpha squared minus 4 times the determinant all over 2. And if I simplify this a little bit more, let's see, this gives me 1 minus 2 alpha plus alpha squared plus 4 alpha minus 16. I believe that is correct. Okay, so if I collect everything, I've got alpha squared plus 2 alpha minus 15. Okay, so this is what I'm working with, and I want to talk about points of bifurcation and what that means. This is really only something that you should do in Maple. It's not something that you're going to want to do by hand, and I want to show you that. I've got a Maple file that will look at this example together. But before we get to that, I want to talk about some interesting points. Okay? Let's start with, to me, one of the more interesting points here is when you have a trace of 0. So your trace is 0 whenever alpha is 1. Do we see that? Now, if we think about the trace determinant plane, when alpha is 1 or when the trace is 0, so having a trace of 0 means that you are on the vertical axis. So these are the value. This value of alpha will put you on the vertical axis, and if I plug alpha equal to 1 into this, that would give you a determinant of 3. Right? So I know that's going to be a center. I know I'm going to have a center behavior there. Okay, what if my determinant was 0? So if the determinant was 0, that means that alpha is 4. And if alpha is 4, then the trace is 3. So determinant of 0 means you're on the horizontal axis. A trace of 3 means you're positive. So this is a nodal source. So we move from a center to a nodal source, okay, So we know we've got at least 2 different points of behavior. The center behavior is key because, well, I shouldn't say, by the way, that this is a nodal source. I should say that it's a 0 eigenvalue source. It would be a nodal source if D was slightly positive there, but because you're on the axis, it's a 0 eigenvalue source and a center. The reason those 2 points, the reason that is important is I know that for this problem, if this were my trace determinant plane, and this is my critical polynomial, then right here, I'm a center, and right here is where that 0 eigenvalue solution is, right? So this is 0, 3, and this is 3, 0. The reason that those are important is they're bifurcation points, because if you move off of them just a little bit, your solution behavior changes dramatically. So if I increase my determinant just a little bit, all of a sudden I'm a nodal source. If I decrease it a little bit, I'm a saddle. Here I'm a spiral source or I'm a spiral sink, right? So I know these are going to be points of bifurcation because they're going to result in changes. Other points where we might have something interesting occur is where we cross the critical polynomial. And that's what this number will tell me. So if I want to, once again, use quadratic formula, I can use it to figure out alpha. Alpha is the opposite of b, plus or minus square root of b squared, which would be 4 minus 4ac. AC 2a. Okay, so I'm just looking at this quadratic here. So this would be -1 plus or minus. If I pull out the 4's in both cases, I'm going to get the 2 to cancel here. So I end up with the square root of 1 plus 15. Square root of 50 is 4, right? So this looks like -1 plus 4. So alpha is equal to 3, or alpha is equal to -5. Okay, so alpha equal to 3, or alpha equal to -5. So if alpha is equal to 3, you can see here the trace is 2. So that's probably that point right there. That's alpha equal to 3. This was alpha equal to 4. This was alpha equal to 1. And then the other point is over here at -5. So alpha equal to -5 would make the trace -6, and alpha equal to -5 would mean that's 9. So that's like right over here. So that's alpha equal to -5. What you kind of have here is a trail through the phase portrait, where as alpha changes, you're ending up at different points in the trace determinant plane. And that's what we're going to use Maple for, is to plot the trail of points that different values of alpha make. But these are your 4 points of bifurcation, and this is how you would find them. So to answer this question, how many points of bifurcation does the system experience? The answer is 4. 4 points of bifurcation. Describe the solution behaviors just before, at, and just after each bifurcation point. Well, you can clearly see here, values of alpha less than -5, they're going to be up in here, so they're going to be, what, nodal sinks? And then you're between alpha -5, alpha 1, you're going to have spiral sinks. Between alpha equal to 1 and alpha equal to 3, you're going to have spiral sources. Between alpha equal to 3 and alpha equal to 4, you're going to have nodal sinks. And past alpha equal to 4, you're going to have saddles. Now to prove that, let's take a look at Maple. All right, so what I have here in this Maple file is the exact same system that we just looked at. And I have an animation of that system so you can see everything I was just talking about. So this is a command that you're going to want to look at when you do your maple file. It'll help you to create animations like this. So this is alpha equal to -6, right? Which we just talked about. Right? So if alpha is -6, right? So if alpha is -6, we're over here, we have a spiral, or we have a nodal sink, right? So we're expecting nodal sink kind of behavior. All right, so you can see that. You've got the one line of eigenvector there. You've got another straight line eigenvector like right around here, and it sinks in over time. Then watch, it goes from sink to spiral sink to center, if I could get it just right, almost to center, right? The value that we had for center was alpha equal to 1. So if alpha is 1, right there, there's our center. And then we said it goes from alpha equal 1 up to alpha equal 3, and it starts to spiral source. But at alpha equal to 3, we have a degenerate source, right? So there's one eigenvector here, one straight line solution, and we've got the degenerate source spiral off of that. And then once it gets past alpha equal to 3, we should have a nodal source. So right there, just briefly, you've got the nodal source. And then if we push it past alpha equal to 4, you have a saddle. So you can clearly see the saddle behavior there forming. So those are all the different parts. If you want to get an even better picture, what I recommend you doing is take and create a function for the trace, create a function for the determinant. These are functions of the parameter alpha. Then plot a sequence of points where you've got different values of alpha. I've done that in this graph. What this graph is it's a plot of the critical polynomial versus a sequence of points defining the trace and determinant. And what you see is you've got one place where we change, a second place where we change, a third place where we change, and then a fourth place where we change. Hence, there are 4 points of bifurcation because we've got 4 different places across which the system will change behaviors. There are a total of 9 different behaviors that are observed for different values of alpha. Now, it could be, here we get almost every single behavior type, but it could be for a given system, you might not see all the behavior types. For instance, what if this line that we plot just looked like this? You would never see a saddle. What if it was some sort of curve that does this, right? Then you might never see, if it starts inside here, you might never see a nodal sink. The point is, you don't have to always be able to change a parameter and get every solution behavior, but anytime this sequence of points crosses the critical polynomial or one of the axes, that's a point of bifurcation. All right, I know that was a lot of material, so I want you to think about some of the things that we've learned. Take a look at this Maple file, start thinking about the Maple lab or the Maple quiz that's due at the end of this week. And if you have any questions, my virtual door is always open. Feel free to email me or stop by office hours 1 to 3, Monday through Thursday. I hope you all are having a great day, and I look forward to talking to you again soon. Bye.